Okay, let's get started. Let's go ahead and get started. We've got a couple things to do next week. As we talked about last week, we've got almost 10% of your course's grade is all due next week, so a fairly big week. You've got checkpoint 2 and your in-class oral presentations of your design concept report. So I think the design concept report is, the design concept presentation, is worth about 50 points, and the checkpoint 2 is worth 20, and then a variety of other miscellaneous things that you have due that week also. Okay, quick reminder, as of about 3 o'clock this afternoon, there are 62 people who hadn't paid for their book. I keep pestering everybody about this because it's a bit of a problem for us. We're being sent a bill for the books from the publisher based on how many people are enrolled. And we have 62 people. That's about $2,000 worth of fees we need to send over to the publisher, but we don't have it, right? We need you guys to pay us, so please do that. Now, the deadline is tomorrow afternoon, essentially when the cashier's office closes. You won't be able to pay it after that. Without being late, and then you'll have, I think, about 2 hours to get it over to us in the EDL. There are penalties for this, and these penalties are essentially going to escalate depending on how long you take to get it taken care of. If you don't have it done by tomorrow at 7 o'clock, you're going to lose all the points for the reading assignments. That's about 40 points right there. And plus, you will not earn any credit in the course until you do get it paid and submitted. And next week, that's about 10% of your grade. So if you're 1 week late in getting this paid, well, first of all, it means you took half the semester to get it done. But if you're 1 week late in getting it paid, you're going to lose almost 100 points that you really didn't need to lose. So please get that taken care of, and you won't have to hear me nag you anymore. I won't be making any more nagging to the whole class, so those of you who have paid it can take a sigh of relief. You don't have to hear me anymore on that. But your grade will rapidly drop, so please get it taken care of. I hate to be the bad guy on this stuff, but I think we've been more than fair in giving you so much time to get it paid. If you're getting nagging emails from me but did pay it already, then please respond to those emails letting me know that there's a problem, and I'll try to work that out as soon as possible. And that's happened for a couple of people. Whether it had been paid was entered into the web campus a bit late, and there were people freaking out about that. So if that's you, then please let me know as soon as possible. So we're halfway through this week, so you probably have already noticed that we're not having skills labs if you showed up. This Friday is another holiday. There will be, the next 2 weeks, all skills labs are going to be on the same weekly schedule. But then after that, I think it's Veterans Day or another holiday's coming up. And we're going to go back to this staggered schedule where Mondays are actually trailing behind the rest of the week. So we'll be back out of sync pretty soon. But for the moment, we are just meeting normally, except for this Friday, which is a holiday. Checkpoint 2, we talked about this last week, so I won't belabor, last class, so I won't belabor this a whole lot. The idea behind this is we want to make sure that you guys aren't taking too long to get up and running with making your purchases of things. So we've had lots of people already do it, get it out of the way. If you haven't done it, then the last point that you can do it is before your class when you do your oral presentation. So not after, it's got to be before class. And if your skills lab starts at 3, you should have done it by 3. Okay? Your TA will hopefully be there a little bit early, or the other people working at the desk in the EDL, they can also walk you through it. So please get that taken care of. We definitely can't have you doing it during your oral presentations. Oral presentations, just as a quick reminder, dress up. Okay? You don't have to wear a suit and a formal gown or anything like that. The idea is that we want you to try to, one, own the stuff, where you can present yourself in a professional manner. And what we mean by that is no sneakers, no tank tops, no short skirts, t-shirts aren't allowed, shorts aren't allowed. In short, something that looks at least business professional, business casual. You don't have to wear a tie. You're welcome to, but you don't have to. You'll probably be expected to wear a tie if you're a guy for some of your presentations in your later courses, your senior design class and things like that. In short, we want you to start getting a good feel for what it means to be professional. And this will be your first opportunity to do this. You won't be the only one there. Everyone in your skills lab will all be dressed up. Hopefully, everyone will be dressed up similarly, so you won't stand out too much. Plan on a 5-minute to 7-minute presentation. If you go any longer than 10 minutes, you'll actually be yanked off the stage, not to mention the penalties on that. In order to figure out how long it's going to take you to do your presentation, you have to rehearse, okay? Not just as you as an individual, but if you're doing a handover to someone else on your team, if you're tag teaming through the presentation, be aware that the tag teaming time itself, the time it takes you to walk to the side and the other person to come to the center and start talking, that can kill 30 seconds. And trust me, teams rarely go too short. Almost everybody takes too long. So you won't discover this until you actually rehearse and try it a little bit. Please look at Chapter 12 in the textbook just as a brief reminder of the types of things that you want to pay attention to. So, first clicker question for today. I'd like a little bit of feedback on how we approach doing the book this year. As you know, we're using an electronic textbook, and the motivation behind that was to cut the costs. In short, the $25 for the electronic version of the textbook is approximately half of what it cost students last year, where the book was actually done in print and done through the student bookstore, where they had their markup over at the bookstore. And we have a variety of alternatives, paperback, hardcover, electronic. I'd just like to know what your opinions are on this. What's the best approach to doing this? And no, I can't give you option 4, which is completely free. Right? So. Excuse me. Okay. So, looks like we have a majority of people who favor the low-cost version, the electronic version, but still about a quarter of the class would have preferred a paper version provided to you. Okay, well, that's useful information for us to have. We've gotten mixed feedback, and we've also gotten some suggestions of trying to have the electronic version available in a Kindle format or an iBooks format or with hypertext or videos embedded into the book and things like that. And before we start investing a lot of time and energy into making revised versions of the electronic version, we wanted to make sure we were on the right track. And it looks like at least 3/4 of you favor the low-cost version. And based on the fact that 50 of you haven't paid for it, I think you'd have preferred a free version completely. So, all right. So last class, Dr. Volstead went over the first few of the engineering grand challenges with everybody, and we, come on. No. And we have 14 of these all told. We have a little bit of history on this if you haven't had a chance to look at the background on it. These grand challenges were put together through a brainstorming session of people essentially from around the world. But it was put forth and sponsored or advocated by what's called the National Academy of Engineers. And this National Academy is essentially the best and the brightest of our nation. It's a group of a few hundred, I don't remember exactly how many there are right now, a few hundred engineers who are nominated by their peers either in industry or in academia or in national labs or by government representatives, who are essentially the best and brightest. And their job was to put together these recommendations to try to identify the strategic areas that our country wants to focus on in the future. And I guess by inference, the rest of the world also, generally their interests are at least not all that far apart from what ours are. And I would have said, had I given this talk 3 weeks ago, that there's only one person in the state of Nevada who's on this National Academy of Engineers. He happened to have, rest his soul, he passed away 2 weeks ago. His office is right next door to mine. This is a pretty lofty crowd. These are the best and the brightest. They're the equivalents of the people who start major companies or who win Nobel Prizes and things like that. There are no Nobel Prizes in engineering, okay? The highest honor that you can get in the United States for being an engineer is to be elected as a member of the National Academy of Engineers. So this list, a lot of thought by a lot of smart people has gone into this list. Now, not everything on the list is of equal profoundness, okay? Providing access to clean water is not necessarily the same thing as saying that everybody has to have, oh, let's pick one here, secure cyberspace, okay? One thing is a matter of life and death, and the other is a matter of quality of life. Both might have equal economic impacts, or maybe they don't have equal economic impacts. But the idea is that in one way or another, all 14 of these address significant needs or significant opportunity for change in the way we live our lives, and they all involve engineers in a significant way. Okay? So some of these you might wonder, say, well, health informatics, better medicines, for example. Medicines are not always created necessarily by the engineers. There are bioengineers and biomedical engineers who are involved with that. But by and large, we tend to think of some of these things as being related to what the doctors do. Doctors don't invent medicines, frankly. That's not what they do. That's done by biologists. It's done by chemists, by engineers of a variety of different types. So we have to sometimes peel back the surface of these, what we call these things, to figure out where engineering fits into these. And hopefully we can do that over the next 4 years of your education. And starting today, hopefully I can give you a little bit of a sense of that. So next clicker question. Where would you think, from what you know, of the global usage of water, what percentage do you think is for personal or household use? This is the water that maybe directly keeps you alive. Okay? It's going to feed directly into the answers of how we address water conservation and things like that. The use of water here in Nevada is obviously a big deal. If you've lived here for very long, you know that. All right, we got some scatter in this one. All right, well, the correct answer is 5%. Only 5% of the water that we use is actually consumed by individuals for household use or for personal use, like drinking water, cooking, things like that. And in some countries where we wash our clothes in the house, that would fit into there. So the vast majority of the water that we use is actually not for personal or household use. What that leaves is industrial use and agricultural use for growing foods and things like that. So if you pause and think about it, that makes sense. We have to irrigate and we have to get water delivered because the need for clean water is such a prevalent and fundamental thing that here in the developed world, here in the US, frankly, Nevada is a little bit more sensitive to this subject than many other states are, but in the United States, we take water for granted, frankly. We don't really have to worry so much about irrigating our crops with toxically contaminated water that's coming from overuse of fertilizers down the road or something like that. But these are real problems in areas of the world where there's a lot of population. Africa, Asia, South America, Central America, even parts of the US where we have water supplies that are contaminated through industrial accidents and things like that. These are big issues because this is one of those of the 14 grand challenges that quite literally is a matter of life and death. There's several of them that are come down to being matters of life and death. And this is one of them that has the potential for such low technology solutions that sometimes people wonder, well, where does the engineer come into this? Okay? Clean water, well, the solution is to not pollute it in the first place. That's right. You know, and to many people, that's what they say. But there are practical constraints. Sometimes the company, the industry that's down the road is already there, and they're not going anywhere. So how do you work around them? How do you purify the water before it leaves their system, for example? Or how do you at least purify the water before you use it? And how do you do this cost effectively? This is actually a pretty big issue, a pretty big challenge, because when we're talking about cost effective, we're talking about systems that are measured in cents, dollars. We don't even get into the dollar range or tens of dollars or millions of dollars range. We're looking for solutions that are really, really cheap. Like, for example, a straw that has a filtration system built right into it where if you had to, and survivalists probably are aware of these people, you go to REI or whatever, you can buy these things to drink out of the stream. But you've probably, I mean, would you want to be drinking out of a bowl like this without having an idea as to what was happening inside that straw? Well, this kid's got some faith, but who knows what she was drinking before she had that straw, okay? How to deliver the water where you want it, pumping issues, filtration, desalination, All these types of things are areas where we want to work on, and there are lots of opportunities for doing it better. Right? In the United States, we don't have to do much desalination, as it turns out. California has some pretty major desalination plants. Middle East has quite a bit also. It tends to work most efficiently in areas where there's lots of solar energy, lots of heat. The process can occur a little bit more easily. But desalination is really the easiest way to make pure water, and we do it from seawater, right? We have an overabundance of seawater. It only works if you live on the coast, obviously. But even if you do live on the coast, getting the pure water away from the salt and delivering that to the people where it needs to go is a pretty significant challenge. In fact, before we did hovercrafts in this class, this was the project. Your team would have been building a desalination system with a variety of design constraints and design objectives relating to what it costs, how easy is it to put together, are the parts available in a third world country? Like if your desalination system requires an iPhone to run, right, that's not practical, right? And you can extend that to many, many other levels where you want to make sure that whatever you make it out of, it's common and cheap and available everywhere. Common and cheap isn't enough. It actually has to be available everywhere. Okay, so just as a quick reminder, and doing it through as a quiz, you have to take a quiz that's going to follow up on everything that we're doing in this, this week's worth of lectures. When is this quiz due? I think we asked this last class, and there was an error in the grade. We'll fix that. Don't worry about it. But we want to make sure you get this, because this is a little bit of an unorthodox way of covering a topic. Usually when we give you a quiz, it's not on something we did in class, but for this one it is. All right, the answer is next Monday. All right, most of you got it. So it's due next Monday, a week from this past Monday, right? Next Monday by midnight. And again, this is a little bit unorthodox for how we are doing our online quizzes. Up to this point, we haven't had any that were based on the class lecture. So I recommend that you look at the website that we point you to at the top of the quiz. Maybe spend some time going over the National Academy of Engineering website. It has a special section on the grand challenges. You can take a look at today's lecture, Monday's lecture, and also the lecture notes, and that should help you get through it. It shouldn't take you long. As far as the quizzes go, it's one of the easier ones of the semester. We just want to make sure that you're at least paying half attention. What? Yeah. Okay, so where we picked up. There are 14 grand challenges, and this is perhaps one of the more, on the surface at least, one of the more mundane sounding ones. But when you pause and think about it, it is one of the ones that has the greatest economic impact in the developed world, at least. Okay? And that is the repair and restoration of urban infrastructure. Right? We have a growing population in this world, and most of that growing population is centering in urban areas. This is where most of the population growth is occurring. In China, which has already got a lot of population, people are moving by the dozens from rural areas into the urban areas. And what this creates is a significant need to find ways of putting people together in high densities of human beings. Lots of infrastructure, roads, transportation, safety things, the ability to get supplies, food, water, delivered into those areas from the areas where they're being produced. Okay? These things involve what we call infrastructure. And this can be anything from highways to bridges to buildings to rail lines to communication systems to transportation networks, air traffic control, the internet, telephone systems, you name it. Okay? It covers all fields of engineering collectively. The civil engineers have a very strong footprint in this area, but frankly, the electrical engineers do as well. The support areas of materials and chemical and mechanical are, of course, in there. And by and large, as it turns out, right now in the United States, most of our infrastructure is decaying. Right? We're still building new stuff. But when we built something in 1950, we were thinking, oh, how long is this going to last? And they were thinking, oh, it'll last for 60 years, no problem. Well, 60 years happened 2 years ago. Okay? And the reason that bridge fell down or the building got rusted or whatever is not because someone screwed up 50 years ago. Well, usually not. It's because products have a natural lifetime. And we have to have designed mortality into our products, designed recyclability, designed repairability. And this was something that we didn't really think about 50 years ago as engineers. We didn't have enough foresight, right? The ancient Egyptians, when they built their pyramids, they were probably thinking forever was the design life for their pyramids, right? But in real terms, they didn't really fully grasp what that meant. Even 50 years ago, when we built a skyscraper, they weren't thinking that that skyscraper was probably going to get knocked down in 50 years or 100 years, or maybe even 20 or 30 years, okay? We have to think about that because that means that has a lot of ramifications to the engineer, not only in terms of how do you take this skyscraper down safely without taking down the entire neighborhood. We learned the way not to do it with 9/11, right? There are ways that are very dangerous. We want to make sure that we build things that can be upgraded, can be repaired as easily as possible and as cost effectively as possible. And nowadays, we're trying to figure out ways to have things become more and more recyclable. The automobile industry is finding new ways to take all of the precious components in a car, like, for example, the electrical components in a vehicle. They tend to have lots of expensive materials in them, gold contacts and integrated circuits, platinum in the catalytic converters, things like that. These are materials that are very expensive. They drive the cost of the car right up front. And they're coming up with new ways to make it easier to take these things out of the car after the car has reached its 10-year, 100,000-mile, whatever design life, right? So they want to figure out, how can we rip out the wiring harness of a car in 30 seconds rather than 3 hours, okay? These types of things apply across the entire spectrum. This notion of green engineering doesn't mean saving a tree, not literally, right? It means, how do we do this most cost effectively so that the materials that we use can be reused? Because obviously, we're going to start running out of this stuff eventually. And we're trying to learn our lessons, because we didn't do that over the recent decades. And we might not need this stuff desperately today, but it doesn't take too much foresight to look ahead and say, at some point, we probably are going to get desperate. We're going to start running out of aluminum. Aluminum's cheap now. We make our tin cans or aluminum cans out of it, right? 30 years ago, we didn't recycle these things because aluminum was cheap. Now we're starting to say, well, aluminum is still fairly cheap, but it's not going to be there forever. It's in our interest to keep all the aluminum together. Let's recycle it as best we can. Same thing with the plastics. We might not have cost-effective ways of recycling all types of plastics, but someday we might. And if we can at least put all the plastic together in a landfill, we won't be contaminating other parts of our environment. And someday we'll have access to these types of things to get the most that we can out of it. So our infrastructure encompasses so many things. And as you might imagine, these are some of the most expensive things we have in our country. The roads, the buildings. The cost of a road is astronomical to build it these days. When I was actually I was even younger than you, I was blown away by the fact that they're estimating that to build a 4-lane highway cost $1 million a mile. That was 20 years ago. I don't even know what it is now. $1 million per mile, right? Just do the math. Go from here to Sacramento is a lot of money, and it's a lot more nowadays than it was 20 years ago. Advanced health informatics. Now, this is one of those areas where we have lots of room for improvement. We have an aging population, as I think we all know. The baby boomers are now starting to grow old, starting to reach retirement age. They're leaving the workforce, and the bad news for all of us is that their healthcare costs are going to start going up pretty quickly. Right? Me and my generation and your generation, are going to need to figure out how to deal cost-effectively and health-wise effectively with the growing health needs of our country. And then hopefully, by the time we get to that point, these things will all be firmly in place for us. There's a variety of different points of view you can take about how engineering comes into healthcare. And one way that's actually pretty big in terms of the overall, what people now currently perceive as wasted costs in healthcare. If you watch any of the presidential debates, they're always going to claim that. Healthcare is too expensive. We're going to save X billion, trillion dollars by turning all of our paperwork into electronic format. Right? That's one thing that they say. Cutting out the middleman or middlewoman. Right? This is information technology. This is computer science. It's programming. And in some cases, it deals with electrical engineering when you're trying to develop devices that can handle this information effectively. Information technology is one way to save a lot of money. Okay? This type of stuff not only can save individuals money, but the more integrated we are, guys, if we can keep the talking down, the more integrated we have our healthcare system, the better we can improve health globally, okay? It wasn't too long ago, 1918 I think it was, where upwards of 20 million, I don't know, whatever it was, a large chunk of people on the planet died of the flu, okay? I'm getting over the flu right now. Hopefully I'm not going to die, for my sake. But the idea is that some of these things can get out of control, even unintentionally, not to mention things like bioweapons and chemical weapons and things like that. The ability for us as a society to respond to large-scale health problems is intricately tied to our ability to share information, not only from one wing of your hospital to the other, but from one point on the planet to another point on the planet. We're starting to see these things in the news more and more often. You know, chicken flus or whatever, bird flus, variety of, pick a year and there's some scare about some disease that is being discovered in some isolated area of the world, and we're worried about how fast it's going to take for it to reach the United States, and if it does, how fast is it going to spread once it gets here. There's at least one movie every year on this subject matter, you know, pandemics, epidemics, something spreading, sometimes intentional and sometimes accidental. Information technology is one of the most cost-effective ways we have of dealing with these things. To let people know that there's a problem so they can shut down their airports, for example, so they can share research information gathered by patient 0, who was the first person known to contract it over here. We're going through something similar like this right now with the meningitis scare. I don't know if you've been hearing about this in the news. They're trying to track down exactly where it came from, and they have. Information technology has allowed them to figure out that it happened in some small-scale industrial pharmacy where they mix up drugs in Massachusetts. They've figured that much out right now. Now they're figuring out that it's actually because of some black fungus that got into their processing equipment, and they're able to track it down. They know exactly which lots created the problems. They're now, just this morning I heard on the news, because of this information processing technology, they're able to figure out that the people who are getting the most sickest from it and who are dying the fastest are the ones who had the medicines that were sitting on the shelf the longest, because the bacteria in there had time to grow. Okay? This type of thing is going to help us figure out how to solve these problems, and now we know which batches to look for and things like that. So, engineering better medicines. This is an area that the role that an engineer can play comes in a couple of ways. And the example I'll give here is really in twofold. One, we recognize that medicines don't always work for everybody, right? There's human-to-human variation in whether the medicines are going to be effective or even whether they're going to be dangerous, like allergies, for example, to certain medicines. And the ability to characterize, to measure the patient and to characterize their genetics. In other words, the patient and their genetics aren't quite the same thing. Their genetics tells them something about how they're built, but the patient also builds in information about what environment they live in, what kinds of things they're exposed to on a daily basis, where it doesn't necessarily have anything to do with their genetics, but their work environment or their home environment is exposed to something that might cause a particular problem. The things that engineers can do in this regard relate to building sensors, building devices that allow us to measure these things. About 10 years ago, the US government spent billions, not even millions, they spent billions of dollars to characterize, to measure, to figure out what the human genome looked like, to figure out and measure every aspect of our DNA. And they spent billions of dollars doing this. Information technology, computers, the electrical engineers with their gene sequencing systems have been able to get this down, not to mention the mathematics and the chemists and things like that. They've been able to take this $3 billion system that took 10 years. Actually, they did it much faster than 10 years. The goal was to do it in 10 years, and they actually beat that goal by many, many years. But we're doing it nowadays for $1,000. Right? So what took $3 billion a decade ago is now done for about $1,000 because of the technology that the engineers have been able to do. We didn't invent the DNA stuff, right, as engineers, but we figured out how to break it up into pieces, how to sequence it, and now we're focusing on processing that data effectively. There's billions of base pairs in